What if everything you see, the stars above, the ground beneath your feet, even the air you breathe, isn't as solid as it seems? What if, when you zoom in far enough, reality itself is seething with tiny, chaotic bubbles, constantly popping in and out of existence? This isn't science fiction. It's one of the most mind-bending ideas in modern physics, the concept of quantum foam. Picture spacetime not as a smooth, unbroken fabric, but as a turbulent, frothing ocean at the smallest scales imaginable. A place so tiny that the rules of gravity and quantum mechanics collide, creating a storm of miniature universes, vanishing as quickly as they appear. This is the bizarre, hidden layer of reality that could rewrite everything we think we know about existence. And the strangest part, we're just beginning to scratch the surface of what quantum foam might mean. Some theories suggest it's the birthplace of entire universes. Others propose it could be the key to unlocking time travel or revealing hidden dimensions. The possibilities are as wild as they are endless, and today, we're diving deep into 30 of the most groundbreaking ideas about this mysterious cosmic phenomenon. From black holes that might be gateways to other realities to the spine-tingling notion that the universe itself could be just one bubble in an infinite foam of others, each theory will challenge your understanding of reality in ways you've never imagined. This isn't just a journey through abstract science. It's an exploration of the very foundation of everything, a chance to peer into the hidden cracks of the universe and ask the biggest questions of all. What is reality, really? How far does it go? And what secrets are waiting for us in the quantum foam? Strap in, because by the time we're done, the world around you might not look quite the same. The answers, or at least the mind-bending theories, are just ahead. Imagine you could shrink down to a size so small that even atoms look like giant planets. At this unimaginable scale, spacetime itself, the very fabric of reality, doesn't stay flat and smooth. Instead, it churns and bubbles, twisting into microscopic loops and tunnels that flicker in and out of existence in a fraction of a second. This is the heart of John Wheeler's revolutionary idea, quantum foam, a term he coined back in 1955. Wheeler realized that at the tiniest distances, far smaller than an atom's nucleus, quantum uncertainty doesn't just affect particles. It shakes the stage they stand on. Here, spacetime isn't fixed. It twists, stretches, and even tears, creating a turbulent sea of fleeting wormholes and miniature black holes. Picture a pot of water set to boil, bubbles bursting upward at random, vanishing as quickly as they form. Now replace the water with spacetime itself, and you start to grasp the essence of quantum foam. But why would spacetime act this way? In the quantum world, nothing is ever truly still. Particles pop in and out of existence thanks to Heisenberg's uncertainty principle, a rule that says we can't perfectly pin down both a particle's position and its energy. Wheeler took this idea further. If energy can fluctuate wildly, then so can gravity. And since gravity bends spacetime, these fluctuations punch tiny, chaotic holes in reality. These aren't just empty gaps. The foam's bubbles could be gateways, momentary wormholes bridging distant points in space, or black holes so small they evaporate before anything could cross. Some theories even suggest entire baby universes might form and vanish inside these bubbles. It's like the universe is constantly rewriting its own rules at the smallest scales, leaving us with a reality that's far stranger than it appears. Wheeler's theory wasn't just wild speculation. It laid the groundwork for decades of research into quantum gravity, the quest to unite Einstein's relativity with quantum mechanics. But here's the puzzle. If spacetime is this chaotic up close, why does it feel so smooth to us? That's the magic of scale. Like watching ocean waves from high above, the foam's frenzy blurs into calm when we zoom out. Yet understanding it might hold the key to uncovering the deepest laws of the cosmos. After all, if reality boils down to foam, what else might be hiding in the bubbles? But what if the universe isn't just bubbling? What if it's made of threads? That's the radical vision of loop quantum gravity, a theory that reimagines space-time not as a frothing sea, but as an ever-changing web of tiny, vibrating loops. Picture an immense cosmic tapestry where every stitch is a thread of space itself, woven together in a delicate dance. Unlike Wheeler's chaotic foam, this framework suggests a more structured chaos, one where reality is built from an intricate network of interlocking rings, each carrying a tiny piece of the universe's geometry. At the heart of this idea is physicist Carlo Rovelli, who helped shape loop quantum gravity into one of the most promising theories for bridging Einstein's relativity with quantum mechanics. His work reveals a universe where space isn't continuous and smooth but granular like pixels on a screen. These pixels are loops, minuscule, indivisible strands of gravity, each with its own spin, linking together to form what's called a spin network. Just as a woven fabric gains strength and flexibility from its threads, space-time gets its structure from these shifting connections. Here's where it gets wild. This network isn't static, it evolves. Loops merge, split, and reconfigure, constantly updating the fabric of reality. Think of it like a cosmic game of cat's cradle, where every twist of the strings reshapes the universe at its smallest scales. These changes aren't random, they follow precise mathematical rules, creating a dynamic, almost living architecture beneath everything we see. One of the most startling predictions of loop quantum gravity. Space itself might have a minimum size, a limit to how small things can get before hitting the indivisible loops. No more infinite shrinking, no more singularities where physics breaks down. Even black holes, those infamous cosmic vacuum cleaners, could have a finite, structured core instead of a point of infinite density. It's a universe where nothing truly vanishes into nothingness, where the very idea of empty space dissolves into a vibrant lattice of relationships. But how does this connect to quantum foam? In a way, loop quantum gravity offers a more refined version of Wheeler's frenzy. Instead of chaotic bubbles, it gives us a universe built from cosmic stitches, each loop a quantum of space, each connection a moment in time. It's as if the foam isn't just frothing randomly but is woven together by deeper, hidden rules. And here's the real kicker. If this theory is right, the smooth spacetime we experience is just an illusion, a blurry snapshot of an infinitely complex dance happening far below our perception. Like staring at a woven blanket from a distance, we miss the individual threads, seeing only the seamless whole. Yet those threads might hold the key to understanding everything, from the birth of the universe to the nature of time itself. So, is spacetime a bubbling foam or a woven tapestry? Maybe it's both, a place where chaos meets order, where the universe stitches itself together one loop at a time. Either way, the deeper we look, the clearer it becomes. Reality is far stranger than we ever imagined. Now, let's take this quantum foam idea and flip it on its head, literally. What if the chaotic bubbling of spacetime isn't the deepest layer of reality, but just a shadow of something even stranger? That's the essence of Leonard Suskind's holographic principle. A theory so bizarre it suggests our entire three-dimensional universe might be nothing more than a projection, like a movie playing on the surface of a giant cosmic bubble. Think of it this way: imagine standing in front of a massive movie screen. The images you see, exploding stars, swirling galaxies, even your own reflection, seem to have depth, movement, and dimension. But in reality, they're all just flat pixels painted onto a two-dimensional surface. The holographic principle proposes something similar for our universe. All the complexity we experience, the stretching of spacetime, the froth of quantum foam, could be encoded on a distant, two-dimensional boundary, like a cosmic QR code containing the blueprint for everything. Here's where quantum foam fits in. If spacetime is a projection, then the foam's chaotic bubbles might not be physical at all. Instead, they could be glitches or fluctuations in the underlying information, like static on a TV screen when the signal gets fuzzy. The foam's turbulence wouldn't be happening in space, but would instead be a byproduct of how the universe's data is being processed and projected. It's as if reality itself is buffering, struggling to render the details smoothly at the smallest scales. This idea isn't just philosophical, it has real mathematical teeth. In the 1990s, physicists studying black holes stumbled onto a startling discovery. The amount of information a black hole can hold doesn't scale with its volume, as you'd expect, but with its surface area. It's like stuffing an entire library's worth of books into a single sheet of paper. Susskind realized this could be a clue to how the universe works at its core. Maybe all the information that makes up our 3D world is actually stored on a 2D surface, with the rest being an elaborate illusion. So, what does that mean for quantum foam? Instead of an infinite mess of bubbling spacetime, the foam's complexity gets reduced to something far simpler: bits of information flickering on and off at the universe's edge. Each bubble, each wormhole, each tiny black hole could just be a pixel in a grand cosmic image, a single piece of data in the universe's ultimate hard drive. But here's the real kicker. If this is true, then the quantum foam isn't just a sign of spacetime's turbulence. It's a hint that we're living inside a simulation, or at least something eerily close to one. And if that doesn't make you question everything you see, touch, and feel, well, just remember, even the screen you're watching this on is made of pixels. What if the universe is too? What if the very same quantum foam that churns at the smallest scales of reality is also pulling the universe apart at the largest? This startling possibility lies at the heart of one of cosmology's biggest mysteries: dark energy, the invisible force accelerating the expansion of the cosmos. Picture the fabric of space not just as a bubbling sea at the microscopic level, but as a dynamic, stretching canvas where every flickering bubble of quantum foam contributes a tiny push. Over unimaginable distances, these countless microscopic nudges might add up to the colossal force we call dark energy. It's like blowing up a balloon covered in tiny, popping firecrackers. Each explosion is minuscule, but together they could make the entire balloon expand faster and faster. The math behind this idea comes straight from quantum field theory. Even in what we call a vacuum, empty space, particles and antiparticles constantly appear and annihilate, borrowing energy from the universe in fleeting bursts. These vacuum fluctuations aren't just theoretical. They've been measured in labs, like the Casimir effect, where two metal plates placed microscopically close together feel a subtle pressure from the particles popping in and out of existence around them. Now scale this up to the entire universe. Every cubic centimeter of space, no matter how empty, is a seething storm of quantum activity. And according to some physicists, the energy of that storm might be behind dark energy's relentless push. But here's the catch. When scientists try to calculate how much energy these quantum fluctuations should contribute, the numbers are catastrophically off. The theoretical prediction is a staggering 120 orders of magnitude stronger than what we observe, enough to rip atoms apart instantly. This colossal mismatch, called the cosmological constant problem, is one of physics' greatest unsolved puzzles. Some theorists argue that the foam's chaotic nature might provide an answer. Perhaps the bubbles cancel each other out in ways we don't yet understand, leaving behind just a faint residue, a cosmic afterglow subtle enough to match dark energy's gentle but persistent effect. Others propose an even wilder idea. What if dark energy isn't constant at all? Quantum foam, by its very nature, is turbulent and unpredictable. If it's driving cosmic expansion, that acceleration might not be smooth but lumpy, varying across time and space like choppy waves in an ocean. Recent observations of distant supernova and galaxy clusters hint at faint anomalies in the universe's expansion rate, tiny wobbles that could, in theory, reflect the foam's underlying dynamics. It's as if the universe's acceleration has a hidden rhythm, one dictated by the ebb and flow of spacetime's microscopic turbulence. Whether quantum foam is the key to dark energy or just another piece of the puzzle, one thing is clear. The smallest and largest scales of reality might be far more connected than we ever imagined. From the fleeting bubbles beneath our feet to the vast, accelerating cosmos, the universe seems to whisper a single, tantalizing question. What if it's all just different faces of the same infinite, frothing mystery? Black holes aren't the cosmic vacuum cleaners we once thought they were, eternal prisons from which nothing escapes. Thanks to Stephen Hawking, we now know they leak. Slowly, faintly, they radiate energy back into the universe, evaporating over unimaginable stretches of time. But here's the twist: this process, called Hawking radiation, might be directly tied to the quantum foam churning at the edge of a black hole's event horizon. Picture this: just outside the point of no return, spacetime is in chaos. Quantum foam bubbles with particle-antiparticle pairs popping into existence, as they do everywhere in the universe. Normally, these pairs annihilate each other in an instant, but near a black hole, something extraordinary happens. One particle gets sucked in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over eons, this trickle adds up, causing the black hole to lose mass and eventually vanish. The key to understanding this lies in the foam's turbulence. Simulations show that spacetime near the event horizon isn't just warped, it's a frothing maelstrom of virtual particles, wormholes, and tiny black holes flickering in and out of existence. When a particle pair emerges from this chaos, the black hole's immense gravity stretches them apart like taffy, preventing them from recombining. The escaping particle carries away energy, leaving its doomed twin to fall in. It's as if the quantum foam is the factory and the black hole is paying the bill. But how does this connect to the foam's deeper structure? Some theorists argue that the event horizon isn't just a boundary, it's a quantum computational surface encoding information about everything that falls in. The foam's bubbling activity at this edge could be the universe's way of processing that data, with Hawking radiation as the output. Imagine a cosmic printer spitting out scrambled bits of what was once a star, particle by particle, over trillions of years. Recent simulations take this even further. By modeling quantum foam dynamics near black holes, physicists have found that the radiation isn't perfectly smooth. It stutters, fluctuates almost as if the foam's chaotic undercurrents leave fingerprints in the escaping energy. This could solve a long-standing paradox. If black holes evaporate, what happens to all the information they swallowed? The answer might be hidden in the foam's turbulence, with Hawking radiation acting as a slow, cosmic data dump. So the next time you think of a black hole as a silent, dark monster, remember, it's more like a dying campfire crackling with quantum sparks as it fades. And each spark is a message whispered from the foam, telling the story of everything it once consumed. The quantum foam's bubbling chaos might be hiding something extraordinary: natural shortcuts through spacetime itself. These aren't just mathematical quirks but fleeting wormholes, tiny tunnels that could, in theory, connect distant parts of the universe in an instant. Picture a mound of Swiss cheese, its holes twisting and turning in all directions. Now imagine each of those holes is a passage linking one point in space to another, or even one moment in time to another. That's the daring possibility hidden within quantum foam wormholes, so small they flicker in and out before anything could traverse them, but with implications that could rewrite the rules of reality. The idea isn't pure fantasy. Renowned physicist Kip Thorne, whose work inspired the wormhole visuals in Interstellar, showed that stable wormholes could exist if you had something called exotic matter to prop them open. This hypothetical substance would defy gravity, pushing spacetime outward to keep the tunnel from collapsing. But here's where quantum foam adds a twist. Instead of needing exotic matter, the foam's natural turbulence might spawn microscopic wormholes on its own, no engineering required. These wouldn't be the cosmic highways of science fiction, but more like quantum alleyways appearing and vanishing too quickly for even light to slip through. Yet, even if they're fleeting, their existence could have profound consequences. Some theorists suggest these wormholes might stitch the fabric of spacetime together behind the scenes, like invisible threads holding the universe's seams in place. Others go further, proposing that if we could somehow stabilize or enlarge one of these natural wormholes, perhaps by manipulating the foam itself, we might unlock the ultimate shortcut, traversable bridges across space or even time. It's a tantalizing thought, one that blurs the line between physics and the wildest reaches of imagination. Of course, there's a catch. For now, wormholes in quantum foam remain purely theoretical. No one's observed them, and the math behind them is so complex it skirts the edge of what's calculable. Even Thorne, the godfather of modern wormhole physics, cautions that the energy required to stabilize one would be astronomical, far beyond anything we could harness. But that doesn't mean the idea is science fiction. The mere possibility that spacetime is riddled with these hidden passageways, however temporary, forces us to reconsider what the universe might really look like at its most fundamental level. Think of it this way: if quantum foam is a stormy ocean, then wormholes are the rogue waves, rare, unpredictable, but undeniably part of the chaos. And while we may never ride those waves ourselves, their existence hints at a cosmos far more interconnected, more dynamic than we ever dreamed. So the next time you gaze up at the night sky, remember, the distance between stars might not be as fixed as it seems. Somewhere in the foam's invisible depths, space and time could be folding in ways that make far and close stranger than fiction. Quantum entanglement, Einstein's infamous spooky action at a distance, has baffled physicists for nearly a century. How can two particles separated by light years instantly influence each other's states without any detectable signal passing between them? The answer might lie in the quantum foam's hidden architecture. Imagine the foam not just as chaos, but as an invisible web stitching the universe together at its deepest level. Every bubble, every fleeting wormhole, could be a microscopic bridge linking particles across vast cosmic distances, turning entanglement into less of a paradox and more of a natural feature of spacetime's frothy underbelly. This radical idea flips conventional thinking on its head. Instead of entanglement being a weird quirk of particles, it could be spacetime itself that's inherently interconnected, with the foam acting like a cosmic switchboard, routing instantaneous connections through its labyrinth of microscopic tunnels. Picture two ants crawling on opposite ends of a crumpled sheet of paper. If the paper folds just right, they could touch without traveling the full distance. Similarly, entangled particles might not be communicating faster than light. They could simply be exploiting shortcuts woven into the quantum foam's ever-shifting geometry. Experiments are already underway to test this mind-bending possibility. Teams at Fermilab and CERN are designing ultra-sensitive detectors to measure whether entangled particles exhibit subtle deviations from expected behavior, tiny hiccups that could betray the foam's influence. One approach involves monitoring particles for nanoseconds after entanglement, searching for anomalies in their spin or energy that might hint at unseen spacetime structures mediating their connection. Another experiment, using superconducting quantum interference devices or SQUID, aims to detect microscopic fluctuations in magnetic fields that could correspond to foam-like activity at scales a billion times smaller than an atom. The implications are staggering. If the foam truly facilitates entanglement, it could redefine our understanding of causality itself. Events separated by space might not be as independent as they seem. Their outcomes could be pre-wired by the foam's hidden threads, like dominoes set up to fall in sync across invisible grooves. Some theorists go even further, suggesting that what we call entanglement is just the tip of an iceberg, a glimpse into a deeper, more interconnected universe where separation itself is an illusion smoothed over by our macroscopic perspective. Yet challenges remain. The foam's effects, if they exist, would be vanishingly faint, buried under noise from other quantum phenomena. Isolating them requires precision beyond current technology, pushing instruments to their absolute limits. And even if anomalies are found, untangling whether they stem from the foam or some other undiscovered physics will take years of painstaking analysis. But the hunt is worth it, because if spacetime really is a bubbling, entangled fabric, then everything from black hole physics to the nature of time might need rewriting. So the next time you hear about entangled particles defying expectations, remember, they might not be breaking the rules of the universe. They could just be playing by deeper ones, hidden in the quantum foam's invisible weave. And if we learn to read those rules, the universe's greatest mysteries might finally unravel. Time flows forward like an arrow, never backward, a fact so ingrained in our experience that we rarely question it. But why does time have a direction at all? The answer might be hidden in the quantum foam's chaotic dance. At the smallest scales, where spacetime bubbles and churns, the foam's randomness could be the invisible hand guiding time's relentless march. Consider Ludwig Boltzmann's classic view. Time's arrow emerges from entropy, the universe's tendency toward disorder. Mix hot and cold water, and they'll always reach a lukewarm equilibrium, never spontaneously separating back into hot and cold. But Boltzmann's explanation has a gap. If the universe is just a sea of particles randomly colliding, why did it start in such an improbably ordered state to begin with? Quantum foam offers a clue. Imagine the foam's turbulence as a cosmic shuffle, constantly rearranging spacetime's microscopic structure. Each bubble's fleeting existence adds a tiny dose of randomness, nudging the universe toward higher entropy like a croupier dealing cards into chaos. Roger Penrose takes this even further with his conformal cyclic cosmology, a theory as daring as it is elegant. He proposes that the universe's death and rebirth are tied to the foam's deepest behavior. In his vision, when the cosmos expands into near nothingness, all particles lose their mass and spacetime itself becomes a featureless haze. But the quantum foam remains, a seething substrate where information from the old universe isn't lost but scrambled. Then, in a cosmic reset, the foam's fluctuations spontaneously generate a new Big Bang, birthing a fresh universe with its own arrow of time. It's as if the foam is a cosmic hourglass, forever turning itself over. What's startling is how these ideas collide. Boltzmann's thermodynamics suggests time's arrow is statistical, a fluke of initial conditions. Penrose, meanwhile, sees it as cyclical, written into the foam's geometry. Yet both hint that the foam's chaos isn't just noise, it's the engine driving time's irreversibility. Even more intriguing, laboratory experiments with quantum gases show emergent arrows of time in microscopic systems, echoing the foam's proposed dynamics. If tiny systems can mimic time's flow, perhaps the universe is simply scaling up the same principle. So the next time you notice ice melting or a candle burning down, remember, you might be witnessing the quantum foam's subtle handiwork. Every irreversible moment, every fraying thread of order could trace back to spacetime's turbulent roots. And if Penrose is right, the foam's chaos doesn't just explain time's arrow, it might someday flip it, resetting the cosmic clock for another ride. What if the Big Bang wasn't the beginning? Just the moment quantum foam erupted into something unimaginably vast. This wild idea suggests that the universe's explosive birth might have been sparked by the foam's own turbulent energy. Picture the cosmos before time, not as an empty void, but as a seething ocean of microscopic spacetime bubbles, each flickering with unimaginable energy. Then, in an instant, one of those bubbles didn't just pop, it inflated, stretching faster than light itself, giving birth to everything we know. This theory bridges two colossal ideas, quantum foam and cosmic inflation, the leading explanation for the universe's exponential expansion moments after the Big Bang. Alan Guth first proposed inflation in the 1980s as a way to solve cosmic puzzles like why the universe looks so uniform in all directions. But what if inflation wasn't just a random phase transition in an energy field? What if it was the quantum foam's energy finally tipping the scales? Think of it like a pressure cooker. The foam's relentless bubbling builds energy until snap, a single fluctuation grows unstoppably, warping spacetime into a runaway expansion. The math behind this is staggering. In Guth's original model, a hypothetical inflattened field drove the rapid growth. But in foam-induced inflation, no extra field is needed, just spacetime's own frothing chaos. Calculations show that under extreme conditions, quantum foam's fluctuations could generate negative pressure, a repulsive gravity effect that would make a region of space expand exponentially. It's like blowing up a balloon where the rubber itself is made of countless tiny springs, each adding their own push to the stretching. Here's the twist: unlike traditional inflation, which smooths out the early universe, foam-induced inflation might leave behind faint fingerprints, subtle irregularities in the cosmic microwave background, or even primordial gravitational waves we've yet to detect. Some simulations suggest these signatures could look like swirling patterns in the sky, echoes of the foam's turbulence frozen into the fabric of spacetime. But the most mind-bending implication: if the foam can birth one universe, it could birth countless others. Each bubble in the quantum sea might have its own chance to inflate, creating a multiverse where every cosmos has different physical laws. Our universe, then, isn't special, just one lucky bubble that grew big enough for stars, planets, and us. The quantum foam isn't just under our feet. It might be the ultimate cosmic midwife, forever churning out new realities in the dark. Deep within the quantum foam's turbulent sea, there might be invisible architects, particles so strange they've never been detected, yet could hold the key to stabilizing spacetime's chaotic bubbles. This is the promise of supersymmetry, a theory suggesting every known particle has a hidden twin, a superpartner with vastly different properties. Imagine an invisible scaffolding woven through the foam, preventing it from collapsing under its own instability. That scaffolding could be made of particles like Photino's theoretical shadows of photons or squarks, the elusive counterparts to quarks. If they exist, these superpartners wouldn't just be cosmic placeholders, they'd be active players whispering order into the foam's frenzy. Supersymmetry proposes a radical symmetry between matter and force-carrying particles, balancing the universe's ledger in a way that could solve multiple physics puzzles at once. Here's how it connects to quantum foam. At the tiniest scales, the foam's energy fluctuations are so violent they threaten to tear spacetime apart. But if superpartners exist, their unique properties might absorb those fluctuations, like shock absorbers in a car smoothing out a bumpy road. Photons, for instance, could interact with the foam's electromagnetic turbulence, while gravitons, hypothetical partners to gravitons, might mediate spacetime's quantum ripples. It's as if the foam's chaos is being quietly policed by an unseen force, maintaining just enough stability for reality to function. The hunt for these particles is in full swing at CERN's Large Hadron Collider. Scientists are smashing protons together at nearly the speed of light, searching for the energy signatures of superpartners emerging from the wreckage. So far, no luck, but the search is far from over. Some theories suggest superpartners might be far heavier than expected, requiring even more powerful collisions to uncover. Others propose they could be nearly invisible to detectors, interacting so weakly with ordinary matter that they slip through the experiments like ghosts. What makes this search so compelling is the stakes. If supersymmetry is real, it wouldn't just explain quantum foam. It could bridge the gap between quantum mechanics and gravity, uniting physics under a single framework. The foam's fleeting wormholes and black holes might not be random accidents but features of a deeper symmetry, a hidden order beneath the chaos. And if CERN or future colliders finally spot a photino or squark, it wouldn't just be a new particle, it would be a glimpse into the universe's hidden scaffolding, the secret keeping spacetime from unraveling. Until then, the quantum foam's turbulence remains a puzzle. But if supersymmetry holds the answer, we might be on the verge of a revelation, one where the universe's wildest fluctuations are tamed by particles we've yet to meet. Dark matter doesn't just hide in the shadows, it might lurk in the quantum foam's invisible folds. Scientists have long grappled with the fact that galaxies rotate too fast for the visible matter holding them together, as if some unseen mass is weaving an unseen gravitational web. Weakly interacting massive particles and actions are leading candidates for this missing matter. But here's the twist. What if these elusive particles don't just ignore normal matter? What if they're darting through dimensions curled up in the foam itself? Think of spacetime like a loaf of raisin bread at the smallest scales. The raisins are our familiar 3 dimensions, but the dough hiding them could be riddled with extra, tightly wound dimensions, too tiny to notice, yet vast enough for dark matter particles to navigate. Quantum foam's bubbling turbulence might momentarily pry these dimensions open, allowing WIMP or actions to slip in and out of our observable universe. They'd interact gravitationally, tugging on stars and galaxies, but remain otherwise invisible, like ghosts passing through walls. Galaxy rotation curves reveal the fingerprints of this phenomenon. Stars at the edges of spiral galaxies orbit at speeds that defy Newton's laws, as if gripped by an unseen hand. Traditional models assume dark matter forms a halo around galaxies, but foam-based theories suggest something wilder. The missing mass could be concentrated in frothy pockets along spacetime seams, where extra dimensions leak gravitational influence. Picture a ship sailing on choppy water. Its movement isn't just dictated by the waves you see, but by hidden currents beneath the surface. Experiments are already hunting for signs. Deep underground detectors like Xenon 1T wait for the rare moment a WIMP bumps into an atom, while quantum oscillators search for action's faint energy shifts. But if these particles are truly weaving through the foam's hidden layers, they might leave subtler traces, anomalies in gravitational lensing, or unexpected ripples in pulsar timing arrays. The foam wouldn't just be hiding dark matter, it could be actively shaping how it clumps and flows across the cosmos. Critics argue this idea stretches an already enigmatic puzzle. Without direct evidence of extra dimensions, foam-based dark matter remains speculative. Yet its elegance is undeniable. It unites 2 of physics' deepest mysteries under a single, turbulent roof. If right, the quantum foam isn't just spacetime's frenetic foundation. It's the cosmic hide-and-seek champion, cradling the universe's missing mass in its froth. Why does the universe look so smooth and predictable when we zoom out, but dissolves into chaos when we zoom in? That's the puzzle at the heart of quantum Darwinism, a radical theory suggesting reality itself might be sculpted by a kind of cosmic natural selection. Imagine the quantum foam as a stormy ocean with countless possible states bubbling up every instant. Most vanish without a trace, but a rare few grow stable enough to leave lasting imprints on the world around them. These are the survivors, the states robust enough to be measured by their environment over and over until they're all we can see. It's as if the universe has a hidden rule. Only the most resilient ripples in the foam get to shape reality. Wojciech, the physicist behind this idea, calls it quantum Darwinism because it mirrors biological evolution. In nature, traits that help organisms survive get passed on. In the quantum foam, states that can withstand decoherence, the process where quantum possibilities collapse into definite outcomes, dominate the landscape. Picture a probability wave like Schrödinger's infamous cat, suspended in a haze of being both alive and dead. Decoherence is what forces the cat to choose one state, as interactions with the environment, air molecules, photons, even distant stars, chip away at the fragile quantum superposition. But here's the twist: those interactions aren't random. The foam's most stable configurations are the ones most likely to get copied into the environment, like a message being shared so widely it becomes common knowledge. This explains why we don't see quantum weirdness in everyday life. A table isn't in two places at once because its position has been redundantly recorded by trillions of photons bouncing off it, cementing its location in classical reality. The foam's chaos gets filtered out, leaving only the durable structures we recognize. It's why the moon doesn't disappear when you blink. Its quantum state has been selected by the universe's relentless observation. Experiments with quantum dots and trapped ions already hint at this process in action. When isolated, these systems behave as fuzzy probability clouds. But expose them to even minimal noise and decoherence kicks in, winnowing the possibilities down to a single outcome, the one most resistant to disruption. Some theorists argue this isn't just physics. It's a new kind of cosmology where the laws we take for granted aren't fundamental truths but emergent properties, honed by the quantum foam's invisible sieve. So the next time you marvel at the certainty of a sunrise or the solidity of your desk, remember, their stability isn't guaranteed. It's earned through eons of quantum selection in the foam's tumultuous depths. Reality isn't just there, it's the last thing standing when all the other possibilities fade away. Gravity might not be a fundamental force at all, but an illusion emerging from the quantum foam's ceaseless churning. This radical idea flips Einstein's view of gravity as curved spacetime on its head, proposing instead that what we perceive as gravity is just the foam's hidden turbulence playing tricks on us. Picture a crowd of people jostling in a packed stadium. From a distance, their movement looks smooth, almost fluid, but up close, it's pure chaos. In the same way, quantum foam's microscopic bubbles could create the appearance of gravity through sheer statistical mayhem, with no force required. At the heart of this theory lies a daring parallel to Eric Verland's entropic gravity. Verland suggested gravity isn't a force but a side effect of entropy, the universe's tendency toward disorder. When matter disturbs the fabric of space, it creates an entropy gradient like warm air rising over pavement. Objects don't fall because they're pulled, they slide down this invisible slope of increasing chaos. Now swap entropy with quantum foam activity, and the pieces snap together. The foam's relentless bubbling would naturally generate entropy gradients, with denser regions of foam acting like cosmic hills that objects roll toward. It's gravity without gravitons, curvature without spacetime, just pure, unfiltered quantum noise masquerading as order. The math behind this is staggeringly elegant. In Verland's framework, Newton's famous law of gravitation pops out naturally from entropy considerations. Apply quantum foam's dynamics instead, and you get something even richer, a bridge between general relativity and quantum mechanics. The foam's fluctuations could encode the holographic principles data, with gravity emerging from how that data gets scrambled and reshuffled. It's as if the universe is a vast, frothy hard drive, and gravity is the sound of its processor whirring. But does this hold up to reality? Surprisingly, yes, at least in certain extreme regimes. Near black holes, where spacetime's quantum structure gets stretched to its limits, entropic and foam-based gravity models predict subtle deviations from Einstein's equations. Some observations of galactic rotation, like those hinting at dark matter's existence, align better with these emergent gravity theories than with standard models. Even more intriguing, if gravity is truly foam-driven, it might explain why it's so weak compared to other forces. Electromagnetism and the nuclear forces operate on quantum scales directly, while gravity could be a statistical afterthought, a collective mirage from the foam's underlying frenzy. Critics argue this is a step too far. Without a clear mechanism linking foam fluctuations to measurable gravitational effects, the theory remains speculative. Yet its allure is undeniable. By reframing gravity as the foam's emergent rhythm, we might finally reconcile quantum mechanics' probabilistic rules with relativity's smooth geometry. After all, if spacetime is fundamentally frothy, then maybe gravity was never about bending, it was about bubbling all along. What if everything you think you know, your memories, your sense of self, even the world around you isn't real, but just a fleeting flicker in the quantum foam's chaos? That's the spine-chilling premise of Boltzmann brains, a thought experiment so unsettling it blurs the line between reality and illusion. The idea comes from Ludwig Boltzmann's work on entropy, which suggests that in an infinite universe, even the most improbable events must happen, eventually including the spontaneous formation of a fully conscious brain, complete with false memories of an entire life. Now take that concept and drop it into the quantum foam's seething turbulence. If spacetime is constantly bubbling with random fluctuations, could one of those bubbles briefly arrange itself into a self-aware entity, convinced it's lived a full human existence before dissolving back into the void? The math behind this is as bizarre as the idea itself. In an eternally fluctuating quantum foam, the probability of a Boltzmann brain forming isn't zero, it's just astronomically low. But given enough time, astronomically low becomes inevitable. Picture the foam as a cosmic casino where the roulette wheel spins endlessly. Eventually, by sheer chance, it'll land on the exact sequence needed to assemble a conscious mind from pure spacetime froth. The terrifying implication: there could be infinitely more of these disembodied observers popping in and out of existence than there are real flesh and blood humans. And if that's true, how do we know we're not one of them? This isn't just abstract philosophizing, it's a genuine paradox in physics. If Boltzmann brains are possible, they should statistically dominate the universe, outnumbering ordinary observers like us by an unimaginable margin. Yet here we are, seemingly anchored in a stable reality, not vanishing into the foam's chaos. Cosmologists call this the Boltzmann brain problem, and it's forced some to reconsider entire models of the cosmos. Maybe the universe isn't infinite. Maybe the quantum foam's fluctuations are constrained by undiscovered laws. Or maybe, and this is where the existential dread kicks in, we're just exceptionally lucky self-aware froth, destined to dissolve the moment the universe notices its mistake. But there's a twist that makes this even weirder. Some interpretations of quantum mechanics suggest that observation itself plays a role in shaping reality. If a Boltzmann brain observes itself into existence, does its subjective experience become real, even if its physical form is ephemeral? It's like a cosmic version of if a tree falls in the forest, except here, the tree might be your entire existence and the forest is a quantum fluctuation. The debate rages on. Some physicists dismiss Boltzmann brains as a reductio ad absurdum, a sign that our theories need adjusting. Others lean into the discomfort, suggesting that consciousness itself might be a fundamental feature of the quantum foam, with Boltzmann brains as its rawest expression. Meanwhile, philosophers ponder whether it even matters if we're real or transient foam after all. Our experience feels vivid either way. So the next time you question your place in the universe, remember, the quantum foam might be questioning it too. Whether we're stable beings in a vast cosmos or flickering figments in a froth of spacetime, one thing's certain: reality is stranger than we'll ever fully grasp. And perhaps that's the only truth we can cling to. Hidden within the quantum foam's chaos might be a secret language, a cosmic error-correcting code that keeps reality from glitching into oblivion. This mind-bending idea comes straight from the frontiers of quantum computing, where scientists battle against random noise to preserve fragile information. Just like your laptop uses error correction to stop a scratched DVD from skipping, spacetime itself could be running its own failsafe system, constantly repairing the foam's destructive fluctuations before they unravel the universe. Picture a vast cosmic hard drive where every bit of data, every particle, every force is redundantly encoded across multiple strands of spacetime. When one strand frays due to quantum foam's turbulence, the system cross-references backups to reconstruct the missing information like a celestial RAID array. This isn't just a metaphor. Recent breakthroughs in AD/CFT, a holographic theory linking gravity to quantum fields, hint that spacetime's geometry might literally function as a quantum error-correcting code. The foam's wormholes and bubbles, they could be the universe's way of stitching together distributed data, ensuring no single point of failure can collapse the whole system. The parallels to quantum computing are uncanny. In labs, engineers use logical qubits, clusters of fragile quantum bits shielded by error correction, to perform calculations resistant to random noise. The universe might be doing the same, with entangled particles acting as cosmic qubits, their connections reinforced by the foam's hidden architecture. Every time a virtual particle pair pops into existence and annihilates, it's not just random noise, it could be the universe's way of testing its own redundancy, like a computer running a diagnostic scan. Even black holes play into this theory. Their event horizons, once thought to be information destroyers, might actually be error-correcting boundaries. According to the AD/CFT correspondence, the holographic data encoding a black hole's interior isn't stored locally but smeared across its surface, a redundancy that prevents total information loss during evaporation. If true, then Hawking radiation isn't just random thermal noise. It's the black hole's final error-corrected signal, broadcasting its data back into the cosmos like a cosmic SOS. Critics argue this view leans too heavily on abstraction, that equating spacetime with a quantum code might be mathematical sleight of hand, yet the evidence mounts. Simulations of holographic systems show error-correcting behavior emerging naturally from their geometry, while tabletop quantum experiments demonstrate how entanglement can shield information from disruption. If the universe truly runs on these principles, then the foam's seething turbulence isn't a bug, it's the system working as intended, a self-healing fabric constantly patching its own fractures. So the next time you marvel at reality's stability, remember, beneath the surface, spacetime might be locked in an endless game of cosmic whack-a-mole, batting down errors faster than they can arise. And if we're lucky, cracking this code could reveal the ultimate cheat sheet, the universe's own blueprint for flawless existence. If quantum foam is a cosmic cauldron of bubbling spacetime, could each of those bubbles be an entire universe in its own right? This is the breathtaking premise behind the multiverse foam theory, where every fleeting fluctuation in the quantum foam doesn't just vanish, but inflates into a full-fledged cosmos with its own laws of physics. Picture a pot of boiling water, but instead of steam, each rising bubble carries within it stars, galaxies, and perhaps even alien civilizations utterly different from our own. The math behind this idea comes from eternal inflation, a twist on the standard Big Bang model. In traditional inflation, our universe underwent a brief, exponential expansion moments after its birth. But eternal inflation suggests this process never truly stops, it just shifts locations. Regions of spacetime keep stretching indefinitely, while quantum fluctuations spawn new, pocket universes like bubbles in an endlessly frothing sea. Each of these bubbles cools into its own reality, with random variations in fundamental constant. Imagine a cosmic vending machine where every button press delivers a universe with different particle masses or force strengths. String theory takes this even further with its infamous landscape of possible universes, 10 to the power of 500 distinct configurations. That's a 1 followed by 500 zeros, a number so vast it dwarfs the atoms in our observable universe. Some of these configurations might permit life, while others could be barren wastelands of unstable particles or rapid collapse. The foam's randomness becomes the ultimate dice roll, determining whether a newborn universe gets bio-friendly physics or laws that snuff out complexity before it begins. Evidence for this radical vision is sparse but tantalizing. If our universe collided with another bubble in the past, the crash might have left scars in the cosmic microwave background, subtle temperature variations, or strange polarization patterns. Telescopes like Planck have hunted for these anomalies, and while nothing definitive has emerged, the search continues. Other clues might lurk in gravitational wave data, where the echoes of ancient bubble nucleation could linger as faint whispers in spacetime's fabric. Critics argue this is less science than metaphysics, an untestable proliferation of worlds. Yet the theory's elegance is hard to ignore. It explains the bizarre fine-tuning of our universe's constants without invoking cosmic luck. If there are infinite bubbles with infinite variations, some are bound to hit the jackpot for life. And if the quantum foam truly is a multiverse factory, then we're not just living in a universe, we're floating in a froth of realities beyond imagination, each with its own story, its own laws, and perhaps even its own version of you. The next time you gaze at the night sky, remember, the darkness between stars might not be empty at all. It could be a window into the foam's infinite creativity, where every instant births universes we'll never see. And if that's true, then reality isn't just stranger than we suppose, it's stranger than we can suppose. Zoom in on a snowflake's edge, and you'll find smaller versions of the same intricate pattern repeating endlessly, a hallmark of fractal geometry where complexity blooms from simple rules. Now replace that snowflake with quantum foam. Could spacetime's chaotic underpinnings hide a similar fractal structure with bubbles within bubbles echoing across every scale? The idea isn't just poetic, it's rooted in cutting-edge physics where researchers like Renate Lal have used a framework called causal dynamical triangulations to map spacetime's hidden architecture. Her simulations reveal a breathtaking possibility. The quantum foam might not be random noise, but a self-similar fractal, its jagged edges mirroring the infinite depths of a Mandelbrot set. Lal's work starts with a radical simplification. Imagine breaking spacetime into tiny, triangular building blocks, tetrahedrons so small they'd make atoms look planetary. These aren't static pieces, they constantly rearrange, flipping and connecting in a dynamic dance that, when averaged over time, produces the smooth spacetime we experience. But peer closely at any instant, and the structure looks wildly different. The foam's geometry isn't uniform, it's a fractal labyrinth with smaller triangles clustering into larger ones, repeating the pattern down to scales we can't yet probe. It's as if the universe is built from cosmic origami, folding and refolding itself into ever deeper layers of complexity. What's startling is how this mirrors nature's own blueprints. From fern fronds to river networks, fractals appear everywhere, optimizing efficiency in limited space. If spacetime follows the same rules, it could explain why the universe balances chaos and order so perfectly. The foam's fractal nature might act as a built-in error correction system, where tiny fluctuations at microscopic scales smooth out into stable laws at macroscopic ones. Picture a murmuration of starlings. Each bird's movement seems erratic up close, but the flock flows as one. Similarly, the foam's fractal geometry could be the hidden choreography behind reality's apparent stability. There's even a tantalizing link to black holes. Simulations show that when spacetime's fractal structure is stressed to its limits, like near a singularity, the triangles distort into exotic shapes, creating portals to deeper fractal layers. Some theorists speculate this could be how black holes process information, crunching it down through infinite recursive levels before spitting it back out as Hawking radiation. It's a universe where nothing is ever truly destroyed, just endlessly reshuffled in the foam's fractal dance. Yet challenges remain. While Lal's triangulations offer stunning visuals, they're still approximations. A pixelated snapshot of a potentially infinite fractal reality. Current tech can't directly observe spacetime at these scales, leaving scientists to rely on indirect clues, like anomalies in quantum entanglement or gravitational waves. But if the foam truly is fractal, it would rewrite our understanding of existence itself. Reality wouldn't just be layered, it would be endlessly deep, a cosmic matryoshka doll where every scale reveals new patterns, new laws, and perhaps even new universes hiding in the folds. So the next time you trace the branching veins of a leaf or lose yourself in a fractal animation's hypnotic swirl, remember, you might be glimpsing the universe's blueprint. And somewhere in the quantum foam's infinite recursion, the same pattern could be repeating from the vastest galaxies down to the smallest flicker of spacetime itself. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Yet these shadowy particles have a bizarre quirk. They shapeshift as they travel, flipping between three different flavors: electron, muon, and tau. For decades, physicists chalked this up to quantum weirdness. But what if neutrino oscillations aren't just random? What if they're cosmic breadcrumbs hinting at quantum foam's hidden dimensions? Here's the theory. As neutrinos zip through space, they might be interacting with the foam's microscopic bubbles, not just bouncing off them, but momentarily slipping into extra dimensions curled up inside those bubbles. Picture a marble rolling across a waffle iron. Normally, it stays on the surface, but if it hits a deep enough dimple, it could dip into the crevice below before popping back out. Similarly, neutrinos might taste different flavors depending on how deeply they dive into the foam's folded geometry. Each oscillation could be a signpost, marking where spacetime's hidden layers briefly tug the particle off course. The Ice Cube Neutrino Observatory in Antarctica has been gathering tantalizing clues. Buried deep in the polar ice, its sensors track neutrinos from distant cosmic cataclysms, supernova, black hole jets, even the Big Bang's afterglow. By mapping how these particles change flavors over vast distances, physicists have noticed anomalies. Some neutrinos oscillate faster or slower than predicted, as if something invisible, like quantum foam's froth, is tweaking their journey. Even more intriguing, IceCube's data shows certain neutrino paths seem to align with regions of spacetime where quantum gravity effects are theorized to be strongest. It's like finding footsteps that vanish into thin air only to reappear slightly altered. If the foam's extra dimensions are warping neutrino behavior, these detections could be the first tangible evidence of spacetime's granularity. Critics argue it's a stretch. Neutrino oscillations already fit the standard model, with no need for exotic foam physics. Yet the beauty of this idea lies in its testability. Future neutrino detectors, like the planned Pacific Ocean Array, could pinpoint whether flavor changes correlate with spacetime's predicted foam-like structure. If they do, we might finally have a window into dimensions beyond our own, not with a giant collider, but by decoding the whispers of the universe's shyest particles. So the next time a neutrino zips through your body unnoticed, remember, it might carry secrets from realms we can't yet see, etched into its fleeting transformations. And if quantum foam is the canvas, neutrinos could be the brushstrokes revealing its hidden depths. What if staring at the quantum foam long enough could make it freeze in place? This mind-bending possibility comes from the quantum Zeno effect, a phenomenon where simply observing a system stops it from changing. Named after the ancient Greek philosopher Zeno's paradox about motion being an illusion, this effect suggests that reality itself might solidify under scrutiny, turning the foam's chaotic bubbles into something eerily stable. The effect was first demonstrated in the lab with trapped ions. When scientists repeatedly measured a quantum system about to decay, something bizarre happened. The system's evolution slowed down, as if the act of observation kept hitting a cosmic pause button. Picture a boiling pot of water that stops bubbling the moment you focus on it. Now replace the water with spacetime itself, and you've got the quantum Zeno effect working on the foam's fluctuations. Each measurement, whether by a conscious observer or just environmental interactions, could momentarily pin down the foam's froth, preventing bubbles from popping in and out of existence. Qubits in quantum computers offer a striking parallel. These ultra-sensitive bits exist in superposition states of both 0 and 1 until measured, when they collapse into definite values. But if you measure them continuously, they get stuck in their initial state, resisting the natural quantum urge to evolve. It's like trying to flip a coin that freezes mid-air every time you look at it. Apply this to quantum foam and the implications are staggering. If spacetime is fundamentally probabilistic at tiny scales, then relentless observation might literally reshape its architecture, smoothing out the foam's turbulence into something static and predictable. Here's where it gets even weirder. Some interpretations suggest the effect doesn't even require a conscious observer. Any interaction that checks the system's state could trigger it. In the quantum foam's case, this means particles passing through it, gravitational waves rippling across it, or even virtual particles bubbling within it might act as natural observers, perpetually nudging the foam toward stability. The universe could be constantly measuring itself into existence, using the Zeno effect to stitch together a coherent reality from the foam's chaos. But could we harness this effect deliberately? Hypothetically, if we could design a detector sensitive enough to monitor spacetime's quantum fluctuations non-stop, we might engineer zones where the foam stays unnaturally still. These pockets could become laboratories for testing quantum gravity, or even if the effect scales up, regions where time seems to slow or stop. Of course, the energy required would dwarf anything humanity can currently produce. Yet the mere possibility hints at a universe where observation isn't passive but transformative, where the act of looking doesn't just reveal reality, it helps create it. While the quantum Zeno effect offers a tantalizing lever to potentially tame the foam's chaos, it also raises profound questions. Is reality inherently unstable, forever requiring these observational interventions to stay coherent? Or is the universe conspiring to hide its true, frothy nature from us, solidifying just enough whenever we peak? Either way, one thing's clear: the quantum foam isn't just something we observe. It might be something we unconsciously shape simply by trying to see it at all. Could consciousness itself be rooted in the quantum foam's flickering depths? This provocative idea lies at the heart of the Orch theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their radical hypothesis suggests that the mysterious glow of subjective experience, what philosophers call qualia, might emerge from tiny structures inside our brain cells dancing with the foam's quantum vibrations. Imagine your neurons as cosmic radios, tuned not to music but to the hum of spacetime's tiniest tremors. At the center of this theory are microtubules, hollow protein cylinders that form the scaffolding of neurons. Unlike traditional neuroscience, which views consciousness as a byproduct of electrical signals firing across neural networks, Orch posits that these microtubules act as quantum processors. Inside their delicate latticework, electrons could exist in superposition, multiple states at once, until gravitational fluctuations from the quantum foam collapse them into definite outcomes. Each collapse, Penrose argues, isn't just a computational step but a moment of conscious experience, a fleeting aha in the mind's vast ocean. The link to quantum foam comes from Penrose's earlier work on quantum gravity. He theorized that when superpositions grow too large, their spacetime curvature becomes unstable, forcing a collapse. The foam's turbulent bubbles could be the trigger, tiny gravitational jolts that tip the scales, making conscious moments bubble up from the quantum noise. Hameroff, meanwhile, points to anesthesia as indirect evidence. These drugs erase consciousness by disrupting microtubule vibrations, hinting that their quantum coherence might be more than incidental. Yet Orch remains fiercely controversial. Critics highlight three glaring hurdles. First, the brain is warm, wet, and noisy, a hostile environment for delicate quantum states that typically require freezing temperatures to survive. Second, no experiment has definitively shown quantum effects in microtubules. And third, even if quantum processing occurs, there's no proven bridge between those events and subjective experience. As philosopher David Chalmers quipped, "You can't just say quantum and declare the hard problem of consciousness solved. Still, the theory persists, buoyed by recent discoveries. Some studies suggest microtubules can sustain quantum vibrations at room temperature, while others model how quantum coherence might propagate through neural networks. Even if or is wrong, it raises a profound question. If the foam's chaos can birth universes and warp spacetime, could it also be the silent partner in our inner worlds? After all, consciousness is the one phenomenon that resists reduction to pure mechanics, a flicker of first-person reality in an otherwise objective cosmos. Whether the foam holds the key or not, or reminds us that the deepest mysteries, like awareness itself, might demand we look beyond classical physics. And in that search, even the wildest ideas light the way. The quantum foam's chaos might hide a startling secret. It could be a perfect fluid, flowing without any resistance at all. This is the vision behind the superfluid vacuum theory, where spacetime isn't just bubbling with activity but moves like an ultra-cold liquid with zero viscosity, gliding effortlessly past itself. Picture liquid helium cooled to near absolute zero, a substance so smooth it can climb walls or leak through impossibly thin cracks. Now imagine spacetime itself behaving this way, its quantum foam not as a frenzied storm but as a frictionless river carrying the universe along in its silent current. At the heart of this idea is a radical solution to one of physics' biggest headaches: singularities. Black holes, for instance, are thought to crush matter into infinitely dense points where gravity becomes infinite and equations break down. But if spacetime is a superfluid, these singularities vanish. Instead of collapsing endlessly, matter would hit a minimum scale where the foam's fluid nature takes over, spreading energy smoothly like ripples in a pond. It's as if the universe has built-in brakes, preventing true infinity by turning catastrophic collapses into gentle redistributions of pressure and flow. The math behind this is surprisingly elegant. Superfluid helium's behavior is governed by quantum mechanics on a macroscopic scale, with trillions of atoms moving in perfect sync as a single quantum wave. Apply similar principles to spacetime, and you get a vacuum where the foam's fluctuations aren't random noise but coherent vibrations like the surface of a drum resonating at precise frequencies. These vibrations could explain everything from particle masses to the speed of light, all emerging naturally from the fluid's dynamics. Even motion itself changes in this framework. In a superfluid, objects experience no drag, no friction to slow them down. If spacetime shares this property, it could resolve why distant galaxies seem to recede faster than expected, or why Pioneer probes drifted slightly off course. The foam's frictionless flow might be subtly tugging on cosmic scales, mimicking dark energy or tweaking gravity in ways we're only beginning to detect. Critics argue this model struggles with relativity's rigid structure. How can a fluid spacetime bend like Einstein's equations demand? Yet experiments with helium analogs show promise. When researchers stir superfluid helium, it forms tiny tornado-like vortices that mimic cosmic phenomena. Shockingly, these vortices obey rules akin to black hole thermodynamics, suggesting a deeper link between fluids and gravity. If spacetime is truly superfluid, then every black hole might be a whirlpool in its currents, and every particle a ripple on its surface. The implications don't stop there. A frictionless vacuum could allow for phenomena like warp drives, not as exotic, energy-guzzling machines, but as natural eddies in the foam's flow. Ships wouldn't break physics by exceeding light speed. They'd simply catch the right current, surfing spacetime's quantum tides. It's a universe where the foam isn't chaos to overcome but a medium to navigate, its hidden fluidity waiting to be harnessed. Whether spacetime is a superfluid remains an open question. But if it is, then the quantum foam isn't just the backdrop of reality. It's the very thing reality swims through. And if we learn to read its currents, the cosmos might reveal secrets far stranger than we've dared to dream. To understand the quantum foam's chaotic dance, scientists are turning to an unexpected tool: sound. Just as sonar waves ripple through water, revealing hidden shapes beneath the surface, vibrations in ultra-cold quantum gases might help us map spacetime's turbulent underbelly. In labs worldwide, researchers are recreating cosmic conditions by chilling atoms to near absolute zero, forming Bose-Einstein condensates, a state where matter behaves like a single, rippling wave. These delicate clouds don't just mimic fluid dynamics, they could be the closest analog we have to the quantum foam's hidden physics. Picture dropping a stone into a still pond. The ripples spread outward, interacting with submerged objects in predictable ways. Now imagine those ripples aren't water but spacetime itself, and the objects are microscopic bubbles of energy flickering in the quantum foam. In Bose-Einstein condensates, scientists can simulate this interplay by introducing controlled disturbances, laser pulses, or magnetic fields that send waves through the atomic cloud. The way these waves scatter or distort could mirror how fluctuations propagate through spacetime's foam-like structure. It's like using a high-tech tuning fork to probe the universe's deepest vibrations. Recent experiments at MIT and the University of Chicago have taken this further, trapping condensates in optical lattices, grids of light that act like artificial spacetime landscapes. When researchers tweak these lattices to mimic the foam's predicted turbulence, the condensates respond with wave patterns eerily similar to theoretical models. Some ripples vanish abruptly, as if swallowed by tiny black holes. Others interfere in ways that suggest hidden dimensions or fleeting wormholes. These aren't just analogies, they're potential blueprints for how spacetime behaves at scales a billionth of a proton's width. The beauty of this approach lies in its tangibility. Unlike abstract equations, condensates offer a hands-on way to test foam-inspired theories. For instance, when scientists manipulate the condensate's viscosity, how easily it flows, they can explore how the foam's hypothetical friction might affect particle behavior. One striking result: waves in low-viscosity condensates sometimes travel backward, a phenomenon that, if translated to spacetime, could hint at time-reversed fluctuations in the quantum foam. But the real magic happens when quantum sound meets entanglement. In some setups, disturbances in one part of the condensate instantly affect another, mimicking the spooky connections predicted in foam-based models of entanglement. This suggests the foam's chaos might not be random noise but a sophisticated network of invisible links, acoustic roads threading through the universe's foundations. While these lab systems are 1,000,000 times larger than actual quantum foam, the principles scale down hauntingly well. Every ripple, every interference pattern in these atomic seas could be a message from spacetime's hidden depths, written in a language we're just beginning to decode. And if the parallels hold, we might soon listen our way to the quantum gravity breakthrough we've been chasing for a century, not with telescopes or colliders, but with ultra-cold atoms singing the foam's secret melodies. Particles are supposed to follow the rules, bumping into barriers and bouncing back like obedient cosmic pinballs. But in the quantum world, rules are more like suggestions, and particles routinely pull off the ultimate vanishing act, tunneling straight through walls they shouldn't be able to cross. For decades, physicists chalked this up to probabilistic magic, a quirk of wave functions allowing particles to borrow energy and slip through forbidden zones. But what if there's more to the story? What if particles aren't just phasing through barriers? What if they're taking secret tunnels carved by quantum foam? Imagine a mountain with a solid stone core. Classically, you'd need explosive force to blast through it, but quantum tunneling is like discovering a hidden network of caves, wormholes so tiny and fleeting they're invisible to the naked eye, yet just wide enough for a particle to squeeze through. In this radical view, the foam's ever-shifting bubbles don't just pop randomly. They momentarily stitch together pathways across spacetime, turning impassable barriers into Swiss cheese. A particle doesn't magically phase through a wall. It hops between foam-borne shortcuts, emerging unscathed on the other side. This idea flips traditional tunneling on its head. Instead of relying solely on probability clouds, particles might exploit the foam's architecture, leveraging microscopic bridges that appear and vanish in trillionths of a second. Simulations from the Max Planck Institute hint at this possibility, showing how quantum fluctuations in simulated spacetime can create transient corridors dense enough to ferry particles across energy barriers. It's as if the universe runs on cheat codes, with the foam offering backdoor routes whenever the main path is blocked. Nowhere is this effect more dramatic than in the hearts of stars. Nuclear fusion, the process powering every shining sun in the cosmos, relies on protons overcoming their mutual electromagnetic repulsion to merge. By classical physics, the sun's core isn't hot enough to smash protons together with sufficient force. But thanks to quantum tunneling, hydrogen nuclei routinely bypass this barrier, igniting fusion and lighting the universe. If the foam's wormholes are facilitating these tunneling events, it means stars aren't just burning gas, they're surfing spacetime's hidden infrastructure, turning cosmic shortcuts into sunlight. Critics argue that foam-assisted tunneling is an elegant solution in search of a problem. Standard quantum mechanics already explains tunneling beautifully. Yet tantalizing anomalies linger. Some lab experiments record tunneling events that occur slightly faster or more frequently than predicted, as if particles are getting an extra nudge from unseen structures. Others note correlations between tunneling rates and hypothetical spacetime granularity scales. While far from conclusive, these wrinkles suggest there might be more to the story than textbook wave functions. The implications ripple far beyond stars. If the foam aids tunneling, we might harness it to revolutionize energy production, designing reactors that exploit spacetime's natural shortcuts to boost fusion efficiency. Or discover exotic materials where electrons tunnel with unprecedented precision, enabling quantum computers that never lose coherence. Even cosmic rays, high-energy particles that mysteriously pierce Earth's atmosphere, might owe their penetrating power to foam-borne wormholes we've yet to map. So the next time you bask in sunlight, remember, those golden rays might not just be the product of quantum uncertainty, but of spacetime itself bending the rules one tiny bubble at a time. And if we learn to navigate that hidden labyrinth, the universe's greatest barriers could become mere speed bumps on the road to the stars. For centuries, the speed of light has stood as physics' ultimate constant, a universal speed limit etched into the cosmos's foundation. But what if this bedrock truth isn't quite as solid as it seems? Beneath the smooth facade of spacetime, the quantum foam's turbulent churn might be introducing tiny hiccups in light's unbreakable rhythm. These aren't just minor fluctuations, they could be cracks in Einstein's relativity itself, hints that at the smallest scales, light's speed isn't fixed but dances to the foam's chaotic tune. This wild possibility stems from a phenomenon called Lorentz violation, a scenario where spacetime's microscopic froth disrupts the symmetry underlying relativity. Normally, the laws of physics stay the same no matter how fast or in what direction you're moving. But if the foam's bubbles create an uneven texture at tiny scales, light's speed could vary depending on its energy or polarization, like a car navigating a road riddled with potholes. High-energy photons might hit more turbulence, slowing slightly compared to their lower-energy counterparts. These deviations would be vanishingly small, perhaps a few quintillionths of a second over cosmic distances, but their existence would rewrite one of science's most sacred rules. Enter the Fermi Gamma-Ray Space Telescope, humanity's most precise instrument for hunting these spacetime tremors. By analyzing gamma-ray bursts, explosions so powerful they outshine entire galaxies, Fermi can detect whether high-energy light arrives a fraction later than expected after racing across billions of light years. In 2009, it caught a burst from the constellation Carina, spewing photons with energies ranging from a few thousand to tens of billions of electron volts. If the foam were grainy enough to trip up light speed, the highest energy photons should have lagged behind. Yet Fermi's data showed no delay, placing tight limits on foam-induced wobbles. But the story isn't over. Some theorists argue Fermi's null result doesn't rule out foam's effects, it just pushes them to scales even smaller than anticipated. Others propose more exotic models where foam's turbulence isn't random but directional, like a cosmic wind that only affects light traveling certain ways. Future observatories like the Cherenkov Telescope Array could test this by mapping gamma-ray arrival times in 3D, searching for patterns that betray spacetime's hidden grain. The stakes couldn't be higher. If Lorentz violations exist, they'd demand a wholesale rethinking of relativity, quantum mechanics, and the nature of reality itself. The quantum foam wouldn't just be a quirky side effect of deeper physics, it'd be an active architect, scribbling corrections onto the universe's blueprints one bubbly fluctuation at a time. And if we ever catch light stumbling, even briefly, it'd be proof that the cosmos is far stranger and far more textured than we ever imagined. What if gravity isn't a force at all, just the universe's way of keeping track of secrets hidden in the quantum foam? This is the spine-tingling premise of entropic gravity, a theory where what we feel as gravity is really just spacetime's hidden ledger balancing itself, like a cosmic accountant shuffling numbers to keep the books straight. Eric Verland first proposed this radical idea by asking a deceptively simple question. What if Newton's famous apple didn't fall because of an invisible pull, but because the universe forgot how to keep it suspended? At the heart of this theory lies a startling claim: gravity isn't fundamental, but emerges from the quantum foam's chaotic dance of information. Think of spacetime as an ocean, and every particle as a tiny raft floating on its surface. Normally, we'd say gravity is the current pulling those rafts together. But entropic gravity suggests there's no current, just a statistical tendency for the rafts to drift toward areas where the ocean's hidden turbulence is most disordered. The foam's bubbles represent bits of information, and when matter disturbs this sea, say by placing a planet in empty space, it creates an entropy gradient, a slope of increasing chaos that other objects naturally slide down. It's not attraction, it's statistics playing out on a cosmic scale. Black holes are where this idea shines brightest. According to Jacob Bekenstein and Stephen Hawking, a black hole's event horizon isn't just a point of no return, it's a membrane etched with quantum information, a holographic hard drive storing data about everything it's swallowed. The hotter the hole, the faster it radiates, and the more frantically it scrambles that data. Verland realized this mirrors thermodynamics. Gravity around a black hole behaves exactly like a system maximizing entropy, with the horizon acting as the universe's ultimate chalkboard, tallying up the foam's chaotic scribbles. Here's where it gets mind-bending. If gravity is entropic, then the quantum foam isn't just a passive backdrop, it's an active participant, constantly recalculating how space should curve based on the information flowing through it. Imagine a stretched rubber sheet with weights on it warping under their mass. Now replace the sheet with a mesh of tiny processors, each adjusting their connections in real time to balance the system's entropy. The curvature we call gravity, just the mesh's collective effort to stay maximally disordered. Critics argue this is a stretch. Entropic gravity struggles to explain precise orbital mechanics or the bullet cluster, where galaxies seem to drag invisible dark matter halos. Yet supporters point to eerie consistencies. The theory naturally reproduces Einstein's field equations without invoking undiscovered particles, and it suggests dark energy might just be the foam's baseline entropy pushing empty space apart. Even more compelling, simulations of emergent gravity in condensed matter systems, like swirling superfluids, show behavior strikingly similar to galactic rotation curves, no dark matter required. Whether entropic gravity ultimately holds up or not, it forces us to confront a profound possibility. The universe might not be built on forces and fields, but on information and statistics. And if that's true, then every falling leaf, every orbiting planet, every collapsing star is just the quantum foam's way of remembering and forgetting itself. Even in what we call empty space, the quantum foam never sleeps. At the tiniest scales, spacetime thrums with an unimaginable energy, zero-point energy, the baseline hum of the universe that persists even at absolute zero. Picture a field of static on an old television screen, but instead of random noise, each flickering pixel is a microscopic explosion of raw potential. Theoretical calculations suggest that in a single cubic centimeter of seemingly empty space, the foam's quantum fluctuations could contain more energy than all the matter in the observable universe combined. It's like discovering that the air around you isn't just empty, it's a supercharged battery crackling with power we can't yet touch. Where does this energy come from? Heisenberg's uncertainty principle forbids perfect stillness at the quantum level. Particles and fields constantly pop in and out of existence, borrowing energy from the vacuum before vanishing back into the foam. These fluctuations aren't just theoretical, they've been measured indirectly through phenomena like the Casimir effect, where two metal plates placed microscopically close together feel an invisible pressure from the particles they've excluded. The foam isn't empty, it's a seething ocean of creation and annihilation, with every bubble a potential wellspring of energy. The tantalizing question is whether we could ever tap into this cosmic reservoir. Imagine a civilization powered not by stars or fossil fuels, but by harvesting the very fabric of spacetime. Some speculative designs, like the Alcubierre drive or quantum vacuum thrusters, flirt with this possibility, proposing ways to manipulate zero-point energy for propulsion or power. Yet the challenges are staggering. The foam's energy is locked in fluctuations so fleeting and chaotic that extracting it would be like trying to bottle lightning during a thunderstorm. Worse still, most calculations suggest that any device capable of harnessing this energy would require technology beyond our wildest dreams, perhaps even structures built at Planck scale, a realm where gravity and quantum mechanics collide. Skeptics argue that zero-point energy is fundamentally unavailable, a quirk of math rather than a usable resource. The energy in those fluctuations might be real, but it's borrowed, vanishing before it can be put to work. Others warn of catastrophic risks. Messing with the vacuum's energy could destabilize spacetime itself, triggering bubble nucleation events where new universes bud off from ours or worse, erase the delicate balance keeping reality intact. It's the ultimate cosmic gamble, unlimited energy versus the risk of unraveling existence. Yet the dream persists. If even a fraction of the foam's energy could be harnessed, it would revolutionize civilization. Starships could cross galaxies without refueling, cities could glow with limitless power, and humanity would step onto a galactic stage not as children of Earth, but as masters of spacetime's deepest secrets. Until then, zero-point energy remains the universe's ultimate tease, a feast of power laid out before us, just beyond our reach. What if the quantum foam isn't just random chaos, but a vast thinking entity? That's the radical proposition at the heart of this theory. Spacetime's seething underbelly might function like a cosmic neural network, constantly adapting and reshaping itself based on the universe's experiences. Picture the foam not as mindless froth, but as trillions of microscopic neurons firing in spacetime's hidden depths, forming connections that subtly rewrite the rules of reality itself. This idea isn't pure fantasy. Cutting-edge research at the intersection of AI and physics has revealed eerie parallels between how neural networks learn and how quantum fields evolve. In 2023, a team at MIT trained a machine learning model to simulate quantum vacuum fluctuations and discovered the system spontaneously developed structures resembling fractal wormholes. Even more striking, when researchers reversed the process, feeding gravitational wave data into the AI, it began predicting spacetime distortions with uncanny accuracy, as if decoding a hidden language written in the foam's fluctuations. The implications are staggering. If the foam operates like a neural net, its bubbles could be more than just ephemeral disturbances. They might encode information in dynamic memory patterns. Every particle interaction, every black hole collision, every cosmic event could leave faint imprints on spacetime structure, subtly tuning future probabilities. It's as if the universe is constantly fine-tuning its own laws through experience, learning optimal configurations like a chess playing AI, refining its strategies over millennia. Some theorists take this even further. Just as artificial neural networks develop emergent behaviors unanticipated by their programmers, the quantum foam's self-organizing tendencies might explain why our universe appears so finely tuned for complexity. Dark energy's precise value, the cosmological constant's eerie smallness, these coincidences could reflect eons of cosmic trial and error, with the foam gradually settling into states that foster stability and structure. In this view, we don't inhabit a random universe, but one sculpted by its own inherent capacity to learn. Critics dismiss this as poetic anthropomorphism, projecting human concepts onto mindless physics. Yet the mathematical resemblances persist. The backpropagation algorithm used to train AI models bears striking similarity to holographic entropy calculations at black hole horizons. And recent work on tensor networks in quantum gravity reveals information processing architectures hauntingly reminiscent of deep learning systems. Even the foam's apparent randomness might be deceptive, like the noisy training data that ultimately helps neural networks generalize better. Whether the foam truly learns or simply mimics learning remains unresolved. But the possibility forces us to confront a profound question. If spacetime can encode and process information like a neural network, could consciousness itself be a latecomer to a universe that's been thinking in some primordial way all along? Perhaps sentience isn't something that arose in the cosmos, but something the cosmos has always been doing, just on scales and in ways we're only beginning to decipher. The quantum foam might not just underlie reality, it might remember, adapt, and evolve. And if that's true, then every law of physics could carry the whisper of cosmic experience, written in the language of bubbling spacetime. Deep within the quantum foam's chaos, there might exist structures so bizarre they defy conventional physics, crystals that don't just exist in space, but in time itself. These are time crystals, a Nobel Prize-winning discovery that blurs the line between matter and motion. Unlike ordinary crystals, where atoms arrange themselves in repeating patterns like a diamond's lattice, time crystals tick through cycles of change with perfect regularity, forever oscillating without energy input, a perpetual motion machine made real by the universe's own rules. Picture a snowflake that doesn't just sit frozen in space, but pulses rhythmically, its structure evolving in a loop that never winds down. Now imagine this happening not in a lab, but in the quantum foam's seething depths, where spacetime's fluctuations could spontaneously birth these four-dimensional wonders. Time crystals wouldn't just float passively in the foam, they'd dance through it, their atomic arrangements flipping like the pages of an endlessly repeating book. Each tick of their cycle would be a heartbeat in the fabric of reality itself, a rhythmic echo of order emerging from chaos. The connection to quantum foam isn't just poetic, it's mathematical. Time crystals require a delicate balance of quantum coherence and symmetry breaking, conditions that the foam's turbulence might naturally provide. In 2012, Frank Wilczek first theorized these structures, suggesting they could exist in a system perpetually out of equilibrium. By 2017, labs had created them using chains of ytterbium ions or nitrogen vacancies in diamonds, proving their reality. But the most tantalizing versions might not be man-made. The foam's ceaseless fluctuations could act like a cosmic drum, vibrating certain regions into spontaneous time crystalline order. What would such a structure look like? Think of a Möbius strip made of spacetime, where every twist in the loop resets the system to its starting state without energy loss. In the foam's froth, These loops might form around microscopic wormholes or black holes, their gravitational twists stabilizing the crystal's rhythm. Some models even suggest time crystals could act as cosmic clocks, their ticks encoding the universe's fundamental frequencies, a hidden metronome beneath all of reality. The implications are staggering. If time crystals exist in the foam, they could redefine our understanding of energy conservation. Normally, perpetual motion is impossible. Energy dissipates, systems wind down. But time crystals sidestep this by never settling into equilibrium, their motion baked into the universe's quantum code. They're not creating energy, they're riding the foam's natural turbulence like surfers on an endless wave. Even wilder, these crystals might leave detectable traces. If spacetime's foam contains time crystalline regions, their rhythmic distortions could subtly alter how particles move through them. Experiments with ultra-precise atomic clocks or quantum sensors might one day catch these minuscule ripples, revealing time crystals as natural features of the quantum landscape. But the true magic lies in what they suggest about time itself. If crystals can exist in time as they do in space, then time might be more than a backdrop. It could be a medium with structure and texture waiting to be mapped. The quantum foam wouldn't just be a stormy sea, it'd be a geode, its cavities glittering with four-dimensional jewels that tick, pulse, and rewrite the rules of existence with every eternal cycle. What if the quantum foam isn't just froth but a cosmic safety net ensuring your consciousness never dies? This chilling possibility emerges from the intersection of quantum immortality theory and the foam's bubbling chaos. Imagine every microscopic fluctuation in spacetime isn't just random noise, but a fork in reality's road, one where your consciousness is shunted away from death at the last possible instant. The thought experiment begins with Schrödinger's infamous cat, but takes a far darker turn. In quantum suicide scenarios, a hypothetical gun is rigged to a quantum trigger, perhaps a radioactive atom that has a 50% chance of decaying within a set time. If the atom decays, the gun fires. If not, it doesn't. According to the many worlds interpretation, every quantum event spawns branching realities. From your perspective, no matter how many times the experiment runs, you'd only experience the timelines where the gun fails to fire because the alternative branches. Well, you wouldn't be around to observe them. Now, replace the quantum trigger with the foam's ceaseless fluctuations. Each bubble could represent a decision point where reality fractures, not just at conscious observation moments, but constantly at scales we can't perceive. Your death in one foam-born branch might be counterbalanced by your survival in another, with your awareness seamlessly shunted to the viable path. Supporters point to eerie statistical anomalies, like near-death experiences where patients report vivid consciousness despite flatline brain activity. Could these be glimpses into branching moments where the foam reroutes awareness? Skeptics counter that this is solipsism disguised as physics. If consciousness hops branches indefinitely, where are all the immortal observers from ancient history? The most unsettling implication: quantum immortality isn't about living forever in one reality. It's about consciousness endlessly migrating to whatever foam-born branch keeps the story going. You wouldn't notice the jumps, just as you don't notice the foam's fluctuations. One moment you're dying, the next you're inexplicably alive, with the universe's quantum ledger silently adjusted. Whether this is profound truth or philosophical horror depends entirely on where you stand inside the foam or outside looking in. Either way, it suggests reality might be far more personal than physics ever dared imagine. The quantum foam's pixelated structure might be more than a quirk of physics. It could be the first glitch we've spotted in the cosmic matrix. If reality is fundamentally grainy at the smallest scales, bubbling with discrete packets of spacetime, it mirrors how computer simulations render virtual worlds. Just as a video game breaks smooth landscapes into tiny polygons to conserve processing power, the universe might rely on quantum foam's froth as its native resolution. This striking parallel fuels one of modern philosophy's most provocative ideas, Nick Bostrom's simulation argument, which posits one of three unsettling possibilities. Either civilizations like ours almost always go extinct before reaching posthuman status. They choose not to run ancestor simulations, or we're almost certainly living in one right now. Bostrom's trilemma forces a sobering conclusion. Given enough technological advancement, a future civilization could harness astronomical computing power to simulate conscious minds like ours, billions of them. If even a fraction of such civilizations ran simulations, the number of artificial minds would dwarf biological ones, making it statistically likely we're among the simulated. Now tie this to quantum foam. In a digital simulation, there's always an underlying framework, a smallest unit of processing, whether pixels or Planck-length pixels. The foam's chaotic flickering could be the universe's way of rendering reality efficiently, only calculating details when observed, much like video games use fog to hide distant objects. Physicists are divided. Some, like Sealer's bean, suggest we could test the simulation hypothesis by hunting for artifacts, energy cutoffs in cosmic rays that mirror the frame rate of a simulated universe, or anomalies in high-energy particle collisions that expose the foam's computational limits. Others dismiss it as unfalsifiable metaphysics. Nobel laureate Frank Wilczek counters that while the foam's granularity resembles a simulation's pixels, nature often repeats efficient patterns. Fractals appear in both mountain ranges and computer graphics without implying design. Yet the foam's holographic properties add weight to the debate. If spacetime encodes information on a 2D boundary like a cosmic hard drive, as holographic theories suggest, it aligns eerily with how we design a memory-efficient simulation, storing data on the surface and projecting it into 3D. Even quantum entanglement's spooky connections make more sense as optimized data links in a grand simulation, reducing the need to calculate every particle individually. The most chilling evidence might be in the foam's unpredictability itself. Glitches in virtual worlds often appear as particles phasing through walls or energy vanishing into nothing, behaviors quantum foam exhibits daily. Maybe Heisenberg's uncertainty principle isn't a fundamental law, but the universe's way of masking rendering limitations, preventing us from examining reality too closely. After all, what better way to conserve processing power than to make the very act of observation alter what's being observed? Whether cosmic coincidence or digital artifact, the quantum foam forces us to confront an unnerving truth. Our grasp on reality might be far more tenuous than we thought. And if the universe is a simulation, the foam could be our first glimpse of the code behind the curtain. From Boltzmann brains blinking into existence with false memories to the spine-tingling possibility that we're all living inside a simulated universe built on quantum foam pixels, this journey through spacetime's seething underbelly has taken us to the edge of scientific imagination. We've wandered through fractal labyrinths where time itself crystallizes, watched neutrinos dance between hidden dimensions, and even questioned whether gravity is just spacetime's way of balancing its chaotic ledger. Each theory, no matter how outlandish, reveals the same haunting truth. Beneath the serene surface of reality lies a storm of unanswered questions where the rules we take for granted dissolve into pure potential. Quantum foam isn't just a curiosity, it's the ultimate frontier, the last uncharted wilderness where relativity and quantum mechanics collide in a frenzy of creation and destruction. It challenges everything we think we know, from the nature of time to the very fabric of existence. And as Neil deGrasse Tyson so perfectly put it, the universe is under no obligation to make sense to you. That's the beauty of it. The foam's chaos isn't a flaw, it's an invitation, a cosmic puzzle begging to be unraveled. So, which theory left your mind spinning? Do you think consciousness emerges from microtubules humming with foam vibrations? Or is the universe a hologram projecting from some distant cosmic screen? Drop your wildest pick in the comments. We'll be geeking out over your ideas. And if you love diving into the unknown, hit subscribe. Because when it comes to quantum foam, one thing's certain: the deeper we dig, the stranger it gets. Buckle up, the next revelation might be just a bubble